going to work a few extra problems here for the semester final review, although I think the actual hard copies of the reviews are pretty good preparation. So here we have 3 points in the plane, and we want to find the measure of angle P. So to find that angle, we're going to need to know what is PQ and what is PR. We need those vectors. So PQ, we're going to go tip minus tail. 1 minus negative 2 is 3. 5 minus 3 is 2. And PR will be 2 minus negative 2 is 4. Negative 2 minus 3 is negative 1. Then we know that the cosine of theta is PQ dotted with PR. PQ dotted with PR over the magnitude of PQ times the magnitude of PR. So PQ dotted with PR is going to be 3 times 4 is 12. 2 times negative 1 is negative 2. In the denominator, the magnitude of PQ is going to be the square root of 9 plus 4. And the magnitude of PR is going to be the square root of 16 plus 1. So that's going to be 10 over the square root of 13 times the square root of 17. Remember, that's the cosine of theta, or in this case we're calling it P, I guess. So the cosine of angle P. So P is going to be the inverse cosine of 10 over the square root of 13 times the square root of 17. I'm going to give this just in degrees. So going to my calculator, I will go the inverse cosine of 10 divided by the square root of 13 times the square root of 17. And I'm getting about 47.7 degrees. 47.7 degrees. Okay, let's see what else we've got here. Can we find an equation of the plane? I'll shrink this down a little bit. Find an equation of the plane perpendicular to segment AB at its midpoint. So we're going to need to know what is segment AB. So we're going to, I'm just going to think of that as the vector. So negative 1 minus 2 is negative 3. Negative 1 minus negative 3 is a positive 2, and 5 minus 1 is 4. Our midpoint, remember, is going to be the average of those x, y, and z coordinates. So that's going to be 2 plus negative 1 divided by 2, negative 3 plus negative 1 divided by 2, and 1 plus 5 divided by 2. So that point is going to be 1/2, and negative 4 divided by 2 is negative 2, and 6 divided by 2 is 3. Now our plane we want perpendicular to AB. That means that AB is also perpendicular to our plane. And so that is going to serve as our normal vector right there. So we can think of in our AX plus BY plus CZ equals D. That's going to be our equation of the plane. The A, the B, and the C are coming right from here. And we're going to plug this point in to find out what the D is. So it's going to be a negative 3x plus 2y plus 4z equals D. And then I'm going to plug in those numbers. So that's negative 3 times 1/2 plus 2 times negative 2 plus 4 times 3 is going to be our D. So that's negative 3/2 minus 4 plus 12. So that's 8, and 8 minus 1.5 is going to be 6.5. Or I guess we could think of that as 13/2. So far we've got that our plane is going to be negative 3x plus 2y plus 4z is equal to 13 halves. And it might look a little nicer if we multiply through by 2, get rid of those fractions. Any multiple will work. So negative 6x plus 4y plus 8z equals 13 might be a more aesthetically pleasing version of that equation of the plane. Okay, let's see if we can graph this next one. So this now, if you recall, is what's called a Lemnos Gate. So this is a Lemnos Gate. And so it's going to be that thing that looks like a figure 8. It's either going to be oriented on the x or it's going to be oriented on that pi over 4 angle. And because it's a sine, then we know that the sine of 2 theta will be equal to 1 when 2 theta, that's the largest that sine can be, and that's going to be when 2 theta is pi over 2 or when theta is pi over 4. So that's going to tell us that our Lemnos Gate, that propeller blade or figure 8, is going to be oriented along that angle theta equals pi over 4. And if we square root both sides, we'll get that r is 3 times that square root of sine of 2 theta. So since the biggest sine can be is 1, the biggest r can be is 3. So if we imagine going out here a length of 3, and similarly 3 going in the negative direction, then we're going to get our kind of propeller blade or figure 8 that's going to go through those points. That's about all we have to do for a Lemnos Gate. Okay, let's see if we can find the area of a parallelogram with vertices A, B, and C given as that. So we have some parallelogram here in space, and if I think of this as A and B and C, then I don't know what D is, but that's okay. If I can find, say, vector AB and vector AC, then the magnitude of that cross product, the magnitude of vector AB crossed with vector AC, that vector will come out perpendicular to those, and its magnitude is going to, the absolute value, and it's kind of weird, the absolute value of that magnitude of that, well, I guess that'll be positive already, is going to be the area that we're looking for. It's going to be the area of that parallelogram. So we need to figure out what is vector AB and what is vector AC. So vector AB is going to be 3 minus 1 is 2, 1 minus 0 is 1, 1 minus negative 2 is 3, and then we're going to get AC, which is negative 2 minus 1 is negative 3, negative 1 minus 0 is negative 1, and 0 minus negative 2 is 2. So remember that to get the cross product vector, AB crossed with AC, we're going to do this 3 by 3 determinant. We're going to call the top row IJK, and then we can go 2, 1, 3, there's vector AB, and negative 3, negative 1, 2 is our vector AC. So expansion, using expansion by minors along the top row, we're going to get I times its minor, which is going to be 1, 3, negative 1, 2, minus, because you alternate signs, J times its minor, which is 2, 3, negative 3, 2, plus K times its minor, which is going to be 2, 1, negative 3, negative 1. So going down minus up, that's 2 minus negative 3 is going to be 5I, and then we'll go 4 minus the negative 9, so that's going to be a minus 13J because of that minus we have there. and then negative 2 minus negative 3 is going to be just 1k. So there is our cross product vector, and so the area is going to be the magnitude of that. So that's going to be the square root of 5 squared is 25, 13 squared is 169, and 1 squared is 1. So I guess that's 169 and 1 is 170. So that's going to be the square root of 195. And that's going to be our area of that parallelogram. Okay? So let's see if we can find the roots of negative 16i. So what we want to do is say that, say, x is going to be our, I left off the kind of the important point there. Let's say the fourth roots of, let me write that a little bit better, about the fourth roots of, find the fourth roots of negative 16i. So if we say x is going to be one of the fourth roots of negative 16i, and we're going to think of x as being r cis theta, that's its polar form, then we'll get x to the fourth is negative 16i. We're going to write both sides of this equal sign in polar form. Since x was r cis theta, when we take it to the fourth, that's going to be r to the fourth cis 4 theta. And I like to think of graphing negative 16i is going to be down here, negative 16. And so that's going to have an r value of 16, and the theta is going to be 3 pi over 2 to put it on that negative imaginary axis. Okay. Then we can say r to the fourth is 16, and we can say 4 theta is going to be 3 pi over 2, and then we'll say plus 2k pi, where k, since we're going to have 4 fourth roots, we can go from 0 to 3 for k. So r is going to be 2, taking the fourth root of both sides. Theta is going to be, when we divide by 4, that's going to be 3 pi over 8 plus, and that's going to become 2 fourths, so that's going to be pi over 2 times k, and again, k is going to go from 0, 1, 2, 2, 3. Does that sound right? I think so. So we're going to get one of our fourth roots is going to be r, which is 2, cis, which is our, we'll choose k to be 0, is going to be 3 pi over 8. Our second one is going to be r, which is 2 again, cis, and then 3 pi over 8 plus pi over 2 is another 4/8, so I think that'll be 7 pi over 8. And our third root is going to be 2 cis, and we'll add another 4 pi over 8 to the 7/8 makes 11 pi over 8. And finally, adding yet another pi over 2 to that, which is 4/8, will be 15 pi over 8. Now, if these were nice numbers, I'd ask you for the rectangular form as well, and you would have to convert that into 2 cosine of 3 pi over 8 plus I sine of 3 pi over 8, just reminding you what that cis stands for, cosine theta plus I sine theta. And we could do this on our calculator, but that's kind of a pain. So we'll just stop here. Okie doke. So can we try to figure out how to do these without using L'Hopital's rule? So this is, the first one is a limit we've seen before in various forms. So we're going to notice that that denominator, what's in that radical, can be written as x plus 2 quantity squared. And then we will try to remember that the square root of x plus 2 squared is not just x plus 2, but actually it's going to be the absolute value of x plus 2. So what we'll see is as we take this limit as x approaches negative 2 from the left, if we plug in something a little bit smaller than negative 2, like say a negative 2.1, we'll get a negative 0.1 in the numerator. The absolute value of negative 0.1 will be a 0.1 in the absolute value. Those will cancel and leave negative 1, and that will be a 1/3. So I'm going to say that's going to be a positive 1/3 on the left. The limit as we approach negative 2 from the right of this thing. So now imagine we plug in something like a negative 1.9. That would be a positive 0.1 in the numerator and also a positive 0.1 in the denominator. And the absolute value would still be positive 0.1. They would cancel and we would get a negative 1/3. So that would mean that the limit as x approaches negative 2 of that function that we've talked about here, since the left-hand limit is different than the right-hand limit, it does not exist. And I'll just say because the left-hand limit and right-hand limit are not the same. Okay, the next one, when we plug in 0 initially, we'll just get 0 over 0, which is indeterminate. Our trick here, if we're not going to use L'Hopital, is to rationalize the numerator. So we will multiply top and bottom by 1 in a form that looks like the conjugate of that numerator. So that will give us the difference of 2 squares in the numerator. And in the denominator, we'll just leave this in factored form. We'll see that first the 9's will kill each other off. Once they're out of the picture, then we can cancel those x's, and then we can let x go to 0, and we'll get square root of 9 is 3 plus 3 on the bottom is going to be 1/6. Okay, Kramer's rule, if you recall, means that x will be dx over d, the determinant of coefficients, and y is going to be dy over d. And d is the determinant of coefficients, is going to be just the 4, 3, negative 8, negative 9. The dx is going to be replace the x column by the right-hand side. So that's going to look like that. And the dy means start with the determinant of coefficients d and replace the right side by the right-hand column, the y column, by the right-hand sign of the equal sign. So d, the determinant of coefficients, is going to go down, so that's a negative 36, minus go up is a negative 24, so that looks like a negative 12. The dx is going to be 9 minus 0, so that's going to be 9. And dy is going to be 0 minus 8, so that's going to be a negative 8. So x is going to be dx over d, which for us is going to be 9 over negative 12, which is a negative 3/4. Y is going to be dy over d, so that's going to be a negative 8 over negative 12, which is 2/3. So our intersection, our point of intersection, or our solution, is going to be the point negative 3/4, 2/3. Okay, can we find an equation of the tangent to the curve, the parametric curve, x given by 3e to the 2t and y equals t squared plus t plus 1 at x equals, let me change that to t equals 0. I want that to be t equal to 0. Okay, so we will start with our point. So x at t equals 0, x is going to be 3e to the 0, which is 3. Y is going to be 0 plus 1 is 1. So our point is going to be 3, 1. To find our slope, we need dy dx, and to get dy dx, we need dy dt over dx dt. So let's see, dx dt is going to be 6e to the 2t, and if we evaluate that at t equals 0, that will be 6. The dy dt is going to be 2t plus 1, and if we evaluate that also at 0, that is going to be 1. So I guess our slope is dy dt, which is 1, over dx dt, which is 6, and again, there's our slope. So our tangent line is y minus 1 is equal to 1/6 times x minus 3. Okie doke. Let's see what we can do with this next one. We want to find m and k so that f is differentiable at t equals 2. So to be differentiable, it has to be continuous. So we want to first make sure that it is continuous, and then we need the left-hand derivative to equal the right-hand derivative. So first, the continuity piece. When we plug in 2 for t, that left side is going to be e to the 0 is 1 is going to be just m, and we need that to be equal to the right side, and we plug in 2, 2 minus 1 is 1, squared is 1, and so m is going to equal k. Well, that was kind of nice. Now, the second part, we need to take those derivatives. So the first derivative, the derivative of me to the t minus 2 is me to the t minus 2. So that me to the t minus 2, again, evaluated at 2, is going to be just m. And that second derivative, we're going to get, the k is going to hang out. We're going to get 2 times t minus 1 to the first times the derivative of t minus 1, which is 1. When we evaluate this at t equals 2, we're going to get 2k. So we have that m is equal to 2k. So if m is equal to k, and m is also equal to 2k, that means if I substitute that in, 2k is equal to k, that must mean that k is equal to 0. Well, that was kind of a bummer. That means m is 0 also, and this isn't a very interesting problem. That's what happens when you make it up off the top of your head. But that's the process, and that's the main thing. Make sure it's continuous by setting those equal to each other, and then make sure their left and right hand derivatives are equal. Let's do Euler's method here. So we've got a differential equation, dy dx equals 2x minus y, and we know a starting point, f of 2 is 3. We're going to use our delta x as negative 0.5, and we're going to approximate f of 1. So we're going to have to do 2 approximations. So first, we want our tangent line at, so we're going to do the tangent line at the point 2, 3. So that means the slope is going to be from our dy dx. So that's going to be 2 times 2 minus 3. That's going to be 1. So our tangent line is going to be y minus 3 is the slope 1 times x minus 2. Now we're going to use that tangent line and step the x value to the left 0.5. So we were at 2, so now we're going to plug in 1.5 for the x and see what the new y is. So y minus 3 is going to be 1 times 1.5 minus 2. So that means y minus 3 is going to be a negative 0.5. And we'll add the 3 over, and that's going to give us 2.5. So now our new ordered pair, so now we're going to find a new tangent line. This time at our new point, which is 1.5. We've stepped it back 0.5 to the left, and the y value there is 2.5. So we need the slope again. So again, going to our differential equation, 2 times 1.5 is 3, minus the 2.5 is going to make our slope be 0.5. So we'll go y minus the y coordinate, and that new one is 2.5, is going to be 0.5 times x minus our new x coordinate, which is 1.5. This time we're going to step our x back 0.5 from the 1.5, so that means our x is now going to be 1. And we'll solve for the new value of y. So we got 0.5, and if we take 1 minus the 1.5, that's going to be a negative 0.5. So we're going to add our 2.5 to the other side, and that's going to be a minus 0.25, and that means our new y value is going to be 2.25, and so we will say f of, what do we say, 1 is approximately 2.25 using our Euler's method. Okay, let's slide up here. So here is our logistic growth differential equation. So we have dp dt is p over 25 times 5 halves minus p over 4. P of 0 is equal to 3. First, we want to know what's the limit as t goes to infinity. So this is our carrying capacity, and that's what's going to make this be equal to 0. So we can either just set that equal to 0, or eventually we're going to want to factor that out anyway. So if we say that our dp dt is going to be p over 25, and then I'm going to factor the 1/4 out of that, so that will give us a clean p here. When we divide by 1/4, we're going to multiply by 4, so that's going to make our first number 5 halves into 10. So the carrying capacity, or the limit as t goes to infinity, is going to be what makes this equal to 0, and that's going to be 10. So 10 is our carrying capacity. The value of p when the population is increasing the fastest is always half of the carrying capacity, so that's going to be when p is 5. Okay, now we have to go to work, and I'm going to start with this modified, or kind of doctored differential equation here. I think this is going to be a little more friendly form. So that's going to be p over 100 times 10 minus p. So we're going to we'll leave the 1/100th on the right side and multiply the dt over there, and we will divide the p and the 10 minus p to the other side. Then we can integrate both sides. So on that left side, we're going to get, oops, I think that should be a 100th. Sorry about that. So we're going to, on the left side, get a partial fractions integral. So our 1 over p times 10 minus p is going to be a over p plus b over 10 minus p. We'll multiply through by the least common denominator. And so we'll get 1 is equal to a times 10 minus p plus bp. So we can choose p to be 0. That means 1 will equal 10a. So that means a is going to be 1/10. And if we plug in 10, we'll get 1 is equal to 10b, which means that b is also 1/10. So our integral is going to become the 1/10 integral of 1 over p dp plus 1/10 times the integral of 1 over 10 minus p dp is equal to the integral of 1/10 dt, I believe that is. So this will be 1/10 the natural log of the absolute value of p, Now we can do a little u substitution in our head. U is 10 minus p, but then remember dp is going to be a negative 1. So we're going to get an extra negative out of this one, and the natural log of 10 minus p, and that's going to be 1/10 t plus, there's where we're going to put our constant of integration. So the trick here that we want to do, because we want to change the order of this subtraction, so we can multiply through by a negative 10. So that will give us then, it's going to change the order of that subtraction. So I'm going to write the positive 1 first, minus the new negative 1 is the natural log of p, and that will make this a negative 1/10 t, and the c, we haven't plugged any numbers for t yet, or p, so we can leave that just as c. So we can use our properties of logarithms and call this 10 minus p over p equals negative 1/10 t plus c. We can exponentiate both sides, and we'll get out of the logarithm and get 10 minus p over p is going to be c e to the negative 1/10. I'll write it as a decimal, t. So this might be a good place to use our initial condition that p of 0 is 3. So we'll get 10 minus 3 over 3 is c e to the 0. So I guess we're going to get 7/3 is c. So I'm going to bring this up over here. So now we have 10 minus p over p is equal to 7/3 e to the negative 0.1 t. So we'll write this as 10 over p minus 1 is equal to 7/3 e to the negative 0.1 t. We can add that 1 to the other side. So we'll get 1 plus 7/3 e to the negative 0.1 t. We can now take the reciprocal of both sides. Remember, you can't do this independently, so all of this is going to go into the denominator, and then we can finally multiply by 10, and this is going to be our final answer for the equation of our exponent, or our logistic growth equation. All right, so we got one more to do here. We're going to do this integral, and this is one that's going to require a trig substitution. These are always a little bit tricky. So we're going to put theta down here. Because we have a subtraction, the thing that precedes the subtraction, its square root is going to be the hypotenuse. One of these is going to be 5x, and the other one is going to be the radical. I don't have a great success record for these. But if we do this, then we would say that the trig function that connects our x value with the constant would be opposite over hypotenuse's sine, which is what we want. So I lucked into this one. So I'm going to say 5x over 2 is sine theta. That means x will be 2/5 sine theta. That means dx will be 2/5 cosine theta d theta. And if we connect the radical with the hypotenuse, that looks like it's going to be an adjacent over hypotenuse, which is a cosine. So our radical over 2 is going to be the cosine. So 2 cosine theta is going to be our radical. And so our integral is going to become the dx is 2/5 cosine of theta d theta. And our radical is going to be 2 cosine of theta. Looks like the cosines are going to cancel, and the 2's are going to cancel. So we'll get 1/5 times the integral of d theta. So that's going to be 1/5 theta plus c. We'll go back to our, we want to go back to the x's. So looking here, we can see that sine theta is going to be 5/2 x. So theta is going to be arc sine of 5/2 x. And so we're going to get 1/5, and then it's going to be arc sine of 5/2 x plus c. All right, there's a few extra problems to do in review for the semester final.